Hey there, everybody. In this video, we're going to be talking about inverse functions and how to create them and what does it mean to be an inverse function. But before we do, we need to establish what is a one-to-one function. So first off, a regular function means for every x value, there is one y. So one and only one y value. So that means if I look at a data set, right, if I have an xy table, I couldn't have a point say like 2 comma 7 and then further down I say 2 comma 3. Well, the 2 is already mapping to a 7, so I can't possibly have it map to something else. So that's the definition of a function. A one-to-one function, however, there's the old school bell. The one-to-one function, however, instead of having an x can go to only one y, a one-to-one function says that an x can only go to one y and a y can only go to one x. So everyone can be with one and only one partner. No one can repeat values ever. So with regular functions, we establish what's called the vertical line test. And that's where we can take our pencil, hold it vertically, and slide it across a graph. And as we do that, it should only be touching our graph in one spot. For a one-to-one, we have to do the vertical line test as well as a horizontal line test. So we have to move our pencil across and vertically, up and down, and make sure that it intersects our graph once and only once. Now, if the horizontal line test fails, meaning it intersects at more than one point, so multiple places, the inverse function will not be a function. So if it's not one-to-one, the inverse will not be a function. And the reason for that is then we'd have y's mapping to multiple x's. Okay? And in general, an inverse function reverses the order of another function. Essentially, to really boil it down into simplest terms, and upper-level mathematicians are absolutely going to be furious with me for saying this, an inverse function just means you're swapping the x and y values. The input and output switch. Output becomes the input becomes the output. Boom, we've inverted them, aka inverse. Okay? If at any point, by the way, if you need to pause this video to write things down, please feel free to do so. All right, so first let's just see, are these things one-to-one? Well, let me try the vertical line test first. If I run this pencil across, that graph is hitting in exactly one spot. All right, so it passes the vertical line test. So does the second one. If I go horizontal line test now, well, right here, I've got two intersection points, right? It hits the graph there, it hits the graph there. So this one cannot be one-to-one. Let's try this guy. It's only intersecting once, and that's going to continue down here. So this one is, in fact, one-to-one. All right. How do we find inverses of functions? Well, to do it algebraically, here's a quick little step-by-step. Here, instead of saying f of x, we're just going to call it y for simplicity. And then step number 2, that is the big step. Step number 2, you're switching, and I'm going to say invert, right, x and y. And then you're going to solve for y. That means I should see y equals stuff. And then at the very end, we're going to use this notation here of f inverse. This is not f to the negative first power times x. This is f inverse of x, right? Because we would read f of x like that. We would read that as f of x, the function f of the variable x. And this is f inverse x. So that little -1 there, that means inverse. Okay, so here I want to find the inverse of the function and then find the inverse function value evaluated at 5. So I'm going to consider this to be y equals 2x minus 1. And then the inversion step, I'm just going to flip-flop x and y. So x equals 2y minus 1. Nothing crazy. Now I need to solve for y. Well, to do that, I need to add 1 to the other side. So I'll have x plus 1 equals 2y. And I need y by itself, so I'm going to divide out the 2 from everything. So I've got y equals, you could have that on the right side as well, it doesn't matter. I could either say x over 2 plus 1/2, or if you really wanted, you could say y equals quantity x plus 1 all over 2. I personally am kind of lazy, so I like the second one better. So final answer, we should be saying the inverse function of x is going to be x plus 1 all over 2. So we found the inverse function. Huzzah. Now if I need to find the inverse function evaluated at 5, at an input value of 5, I'm just going to plug in 5 for x. So 5 plus 1 over 2. Well, that's going to give me 6. So the inverse function evaluated at 5 is going to equal 6. No, it's not. Holy smokes. What am I doing? 6 over 2. Gee willikers is going to equal 3. Man, that's why we tell you to write in pencil. Am I right? Holy smokes. All right. Next one, we'll go a little bit quickly through this. Let's see, I'm going to kind of skip down here. We're going to invert, so I'll have x equals 1/3 y plus 7. So again, instead of f of x, I'm using a y. And then we switched them. I'm going to move the 7 over, so x minus 7 equals 1/3 y. To get rid of 1/3, I need to multiply by 3. So I have 3 times x minus 7 equals y. All right, my inverse function of x is going to be good old-fashioned distribution. 3x minus 21, boom, celebrate, huzzah. Now if I wanted to evaluate this at a value of 2, we'll just plug in 2. 3 times 2 is 6, minus 21, we can do that easily. Now graphically speaking, if you have a point on a graph, all you have to do to find the point on its inverse is just, again, switch, aka invert, the x and y values. Right, so if I have a graph, the original function, let's say has the point, I'm making this up, 3, 8. Well, that means the inverse function, f inverse of x, is going to have the point 8, 3 on there. If this is done properly, if you graph both of them at the same time, they should be symmetrical about the line y equals x, the identity line, right? It has a slope of 1, a y-intercept of 0. This is going to act as a mirror, so the graphs on each side should create mirror images of one another. To see an example of this, I want to graph 2x minus 3 and its inverse on the same line. So I need to find just 3 points. It could be any 3 points. I'm going to choose nice easy values. I can plug in 0, 1, and 2 pretty easily into this function of 2x minus 3. If I plugged in 0, 2 times 0 minus 3 is negative 3. 2 times 1 is 2. Minus 3 is negative 1. And then that would be positive 1. So I can graph these 0, negative 3, 1, negative 1, and 2, positive 1. Or you could just kind of think of this as, hey, let's go slope-intercept form, shall we? Right? So let me graph one line here. Yay. And now to find the inverse, well, this is easy enough. I just need to take these and flip-flop them. So that's negative 3, 0. That's negative 1, 1. And that's 1, 2. So negative 3, 0 is right here. Negative 1, 1 is right here. And 1, 2 right there. So now if I connect those, if I've done this correctly, they should be mirror images, right? If I fold it along this dotted line right there, these graphs should match up. All right, let's do uno mas example. Let me throw a challenging one. Here you go. Oh yeah. All right, this one, we're dealing with a fraction. Anytime you deal with these, if you're not comfortable with fractions, you can feel free to just graph it and steal the points from your graph. Or you can kind of be strategic, and our denominator here is a 3. So I want all of my numbers on the x's for easy math to be some sort of a multiple of 3, and that includes 0. But for the sake of argument, just so you see another method, let's graph this thing as if we're doing slope-intercept. So I have a y-intercept at positive 1. My slope is 2/3, so I go up 2, it's positive, and over 3. So up 2, over 3. All right, let me steal these values. We have 0, 1. This would be 1, 2, 3, 1, 2, 3. We have 3, 3, right? And if I plugged in 3 here, 2/3 times 3, the 3's cancel. That's 2 plus 1, boom, 3. And then let's go up 2 over 3. And that's going to be 6, 5. All right, that means the inverse is going to have 1, 0. It's going to have 3, 3, and it's going to have 5, 6. Before we get there, though, let me graph our original line. All right, now for the inverse. So this right here, this is our original function. The inverse, 1 comma 0, that's right there. 3 comma 3, right on top of that guy. 5 comma 6. Let's see, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, right there. Connect those dots with a straight line. Holy smokes, I got way out of focus there. There we go. And this was the inverse of x function. So there we go. It's easy as that to graph two of them on the same line. All right, that's it and that's all, folks. As always, if you have any questions, shoot me an email or ask in class. I'll be more than happy to walk you through it.